All right, this is tutorial 5035 MAA, tutorial number 7. And this is about combined loading. I'll have a quick recap of the lecture about combined loading. So remember, we have the internal loads that are of four kind of internal loads. We have normal force, which is always perpendicular, a force that's acting perpendicular to the cut. The shear force, which is acting parallel in the same plane of the cut. The bending moment, which acts around the shear forces and produces a stress that is also perpendicular to the cut. And the twisting torque, which is linearly distributed exactly like the bending stress. And it's acting inside the cut. So it's parallel to the cut, this twisting torque. So how are these forces distributed? So this normal force is always distributed in a constant way along the cut. So the stress, as you can see, it's perpendicular to the cut. So we're talking about normal stress, and normal stress is constant, and it's given by the normal force divided by the cross-sectional area. For shear force, we did this last week. Remember, these shear stresses are distributed in a parabolic way along the section. So in previous years, you might have heard that the average, tau average, is V divided by A, exactly like the normal stress. Here, no, this is not the full story. We now know that this stress is on average, all these arrows are the same, but in reality, what's happening is that these arrows are 0 at the top and bottom edge, and they grow until they reach their maximum at the centroid, and then they start decreasing again until they reach 0 here, exactly like this distribution suggests. For the bending moment, I said earlier that they are linearly distributed. This is the equation of a straight line. You can see here, this is y equals mx, where this is m. And so as you go further and further away from the neutral axis, which is of course at the centroid, as you go further and further away, the stress increases in a linear way. And remember, this I is the second moment of area, so it's geometric property of the cross-section, exactly like A was a geometric property of the cross-section, the area, or this Q and this I. This is the first moment of the shaded area. Remember, the first moment of the shaded area. And I is, of course, the second moment of area, exactly the same as this. For twisting torque, we have that tau is exactly in the same way as sigma here. This shear stress is distributed in a linear way along the entire section. So if you take any diametral line, any diameter, you can always find the distribution of stress that depends on the distance from the center. This R stands for radius, and it's the distance from the center. You have no stress here at the center, and as you move away from the center, the stress increases. So this tau comes from this torque T comes from the integration of this stress distribution. Okay, now we have the recap. We can start solving question 3. It says a 25mm solid steel shaft is loaded and supported as shown in figure 3. The x-axis corresponds to the center of the circular cross-section, rigidly attached to the end plate, and two forces act at the end of the pipe, this 2500 Newton and this 500 Newtons force. 2500 Newtons in the x direction, we have a given set of axes, so we must use these ones that were given. And the 500 Newton acts vertically down in the negative y direction. Considering stress elements at point G and H, so let me show you. Point G and point H are here, And this is the section of interest. So the section we are interested in is this one. Because that's where G and H live. They lie on this section here. In fact, I have also drawn already the cross-section. This is the cross-section of interest. And so we have point G and point H that live inside the same cross-section. I also placed here the coordinates of G and H because they will be useful later. So the X coordinate of G, so this is my origin. The X coordinate of this cross-section is 0. So both of these points have an X coordinate of 0. Then if I draw the y-axis upward and the z-axis leftward, exactly as I have them here, I have that the y-coordinate of H is the diameter phi divided by 2. So it's the radius of the section. And the y-coordinate of G is, of course, 0, because it lies on the origin. And the z-coordinate of H is 0, and the z-coordinate of G is phi divided by 2. It's also the radius. I also can calculate the geometric properties of this cross-sectional area. So I have Iy, which is equal to Iz. So the second moment of area with respect to the y and the z-axis are both pi diameter to the power of 4 divided by 64. And the polar moment of area, remember this, is just Iy plus Iz, which is twice as much. So pi diameter to the power of 4 divided by 32. Of course, finally, the area of a circle is just pi diameter squared divided by 4. Now, we want to find what is the stress state at G and H. So, and we also want to draw it on an infinitesimal. So how do we go about that? First of all, observe that on a certain section, we can at most have 6 loads, so 6 internal forces and moments. So every time you cut something, there is a direction that is perpendicular to the cut. And in that direction will always be the normal force. And there are 2 directions, in this case, Y and Z. Let me do this in blue, light blue. To recall the color scheme I've used here above. So this is the normal force. We have 2 directions, Y and Z, that are inside the plane of the cut. And these are the shear forces, always. And we also have that around the normal force, you always have the twisting torque. And around the shear forces, you have 2 bending moments. Now, these are the all possible internal interactions that can happen at this section. So let's find which one of these. So I have a force in the x direction, a force in the y direction, and a force in the z direction, according to my reference system, a moment around the x-axis, a moment around the y-axis, and a moment around the z-axis. So let's label all of these. These are based on the reference system, but these can also be relabeled according to the internal interactions. So this fx, since x, the x-axis, is exactly perpendicular to the cross-section, this also is the normal force. Y and z are both inside the cross-section. So these are both shear forces. And for the moments, remember, the moment around the normal force is always the twisting torque, so say this T, and the remaining 2 moments are always bending moments. Okay, now that we have this, we can find easily what is the value of these forces. So let's say equals I'll say that the normal force is, of course, whatever force is acting in the x direction. It's 2500 in direction x, so it's positive 2500 newtons. Regarding the shear force, we have negative 500 newtons in direction y. So y is upwards, this force is going down, so we have minus 500 here. And we have 0 for Vz, because as you can see, there are no forces in the z direction, no active forces. Finally, what is the force that is making this section twist? We have two forces. One is parallel to the x-axis, so it doesn't produce any moment with respect to x, but this one is perpendicular to the x-axis, and it's applied at a distance of 75 millimeters, this distance here. So 500 times 75 gives me the twisting torque. Now, the positive direction using your right hand, using the right hand rule, is if you put your thumb around this axis and then you try to rotate your fingers around, you get that the positive rotation is this one that I just signed here. And so this force is also making it rotate in the same direction. So we have a positive moment, is positive 500 times 75 Newton millimeters. And finally, for the last two moments, there is one force that makes it rotate left and right. So this is the positive bending moment. Using your right hand rule, again, you'll find that this is the positive bending moment around the y-axis. So bending left and right, this force is parallel to the y-axis. So this gives no moment around y, but this one is perpendicular to the y-axis, and it's applied at a distance of 75 millimeters. So 2500 times 75 Newton millimeters of torque around the y-axis. And this is also positive because this is the positive direction of the bending moment, and this is making it bend in the same direction as this. So this is also positive. Finally, the last one is mz. So this is the positive moment around z using your right hand rule. And so this force is perpendicular to the z-axis, but it's also passing through the z-axis. So this would cause bending up and down if it was applied at a distance. The distance in this case is 0. So this one gives no moment around z, but this one is applied at a distance of 0.2 meters, also perpendicular to z, but applied at a distance of 0.2 meters. So I will say this is 500 times 200 millimeters, so Newton millimeters, 500 newtons times 200 millimeters. Okay, and it's negative. Why is it negative? Because this force makes this structure bend downward instead of upward. So the moment is against the axis. So let me rearrange these ones to be a bit up. This here, let's see if I can do this. Okay. And so I can close this bracket and place these ones. This is also 500 newtons. All right, now that we have values for these, let's find, well, let me calculate the values first. These values here are, the first value is 2500. The second value is minus 500. The third value is 0. And the fourth value is 37,500. The second to last value is 187,000. 187,500. And the very last value is minus 10,000, minus 100,000. These are the values. And of course, we know that each of these has an associated stress. Now, the top one, now from this we can already calculate the stress sigma in direction x. It's very important that sigma, normal stress means normal to the section, and normal to this section, there is only direction x. So the only possible sigma is sigma x in this case. So let me draw here sigma x, as you know, is n divided by a. Finally, this tau would be in this direction. So tau xy, yxy, so the subscripts, this subscript x means the face with normal x, face normal x, and this one means direction y. Okay, so I'm saying that I am on this face with normal x and in this direction here. So this direction is the other one, this one. So tau xy means that. And of course, in this other direction, we will have tau xz. So tau xy is this, which is Vy Qy divided by Iy t. Let's call it Q. Of course, Q will be different if you are in the Y and Z direction, but this will make the notation a bit easier to manage. Now you have tau xz is exactly the same, so Vz Q divided by Iz t. Then for this tau, now this tau is particular. We don't know yet which direction is this tau, because if this was the torque, as you know, this G will have this tau associated with it, and this will be tau xy because it's in direction y, and this H will have this tau associated with it, and this tau will be tau xz because it's in direction z. So this depends on which point we are looking at. So we can't have a definitive answer for this tau, a definitive direction yet for this tau. So let's say that this is T over J times R. Finally, this is always sigma, and if it's sigma, it's always sigma x. There is no way around it. And this is, let's find, this is my. Okay, so it's my divided by Iy times z. How do I know it is z? Because in the bending left and right, this bending around y, this is the neutral axis. So one side will be in tension, this side here, and one side will be in compression, this side here. But that also means that the distribution is like this. So I have one side in tension, one side in compression like this. So one side would be like that, and one side would be like this. And in this case, this bending left means that this left side is in tension and the opposite side on the back is in compression. So that means that for a positive Z, I need a positive stress, and for a negative Z, I need a negative stress. So in this case, I'm using this with a positive sign. And for sigma X in the other direction, I'm using MZ divided by IZ times Y. Of course, this is the same as above, just different. Now, in this case, we have, this is the neutral axis. So some of it is in tension and some of it is in compression. So 1/2 is in tension, 1/2 is in compression. And in this case, the bottom side, if this was positive, the bottom side will be in tension and the top side will be in compression. But what's happening here is that the force is negative. So the moment is negative. And so that means that to have, the moment is negative. So this is in tension. And to have that in tension, so for positive Y, we need tensile stress. So we must have a negative here, because negative and this negative will give 0. Sorry, will give positive. All right, so let's solve this. Now, to solve this, first of all, remember we can neglect these two because the beam is slender, is considered as slender, so neglect this. And it says here, you may neglect the shearing effect on the cross-sectional area of the shaft due to the 500 Newton load. And this is what we are doing now. We say that these ones are 0. Now, these ones are true for every point. Now, let's substitute the equivalent for G. Let me put this here. So let's substitute the radius of G, the Z coordinate of G, and the Y coordinate of G to find the stress state at G. So for G, for point G, I have that this is sigma X equals the normal force 2500 divided by the area, which is a number. And this number is, according to the solution, 5.1 megapascals. Tau xy and tau xz, due to direct stress, we are ignoring. Tau xy equals 0 and tau xz equals 0. We are ignoring because we said we are neglecting them. Now for G, I told you that since the twisting is happening in this direction, the twisting is happening in this direction. So G, so this is the twisting torque. So that means that G feels tau yz in this direction. So we know tau yz for G. Sorry, tau xz, xy. I'm saying that G feels this one. This is tau on phase X in direction Y. And it's a negative stress. It's a negative stress because it's in the opposite direction of Y. In this case, we have tau xy equals negative T over J times R, which is 12.2 megapascal. How do I know it's negative? Well, I know it's negative because this is a positive quantity and the radius. So for the radius of G, again, it must be giving me this stress here, which is opposite to Y. Let's look at sigma X. The first sigma X from the bending moment is my, which is this number, divided by iy, which is another number which you can find from this, times the z coordinate of G. Now the z coordinate of G is phi divided by 2. So these are all numbers. And if I do the calculation, I get 122 megapascals. And finally, for the last one, sigma X of here, I need this number divided by iz times the y coordinate of G. Now the y coordinate of G is 0. And so that means that sigma X is 0 because G is exactly on the neutral axis. For this bending motion up and down, G is exactly on the neutral axis. So it doesn't feel this effect of bending, this bending effect. Okay, this is what's happening to G. Let's see what's happening to H. So I just repeat the analysis for a different point H. And then I have that, of course, sigma X, since it's constant over the section, is exactly the same as G. Tau xy, tau xz for direct shear stress, we said, can be neglected. Tau xy, in this case, is not tau xy, because remember, this is the twisting torque we are looking at. So the tau in consideration is this one, which is a tau xz, and it's positive because it's the same direction of z. So in this case, tau xz, it's the same, is exactly the same because it's at the same distance. See, T over J is the same, and the radius of G is the same as the radius of H because they are both on the outermost fiber of the circumference. So this is also 12.2 megapascals. And finally, sigma X is my over iy times z. What is the z coordinate of H? Z coordinate of H is 0. So this one is 0 now. We can test that. We can test that because for this bending that we are considering, bending left and right, H is exactly on the neutral axis for this bending. So it doesn't feel the effect of that bending at all. But it does feel the tension from this bending down of the structure puts this top fiber in tension, and it's in tension by mz. So negative, negative, positive. It's y. The y coordinate of H is this one. So in the end, we should get 65.2 megapascal according to the solution. Now we can just draw both of these stress states on an infinitesimal. Let me draw the infinitesimal, let me draw it larger. So this is the infinitesimal on around G. And around G, we have that this infinitesimal is, let me check G. If I look at G here, G has the x-axis along this direction. G has the x-axis along this direction and the y-axis along this direction. So I can just draw this x-axis and y-axis. And so I have that sigma x is, of course, the sum of these two. These are the same nature of stress, so I can sum them up. So 122 plus 5.1 is 127.1 megapascal, and this is sigma x. And of course, I have a sigma x exactly in the opposite direction to balance it out. There is no sigma y, as you can see, so I don't put anything in this direction. And tau xy is negative. So tau xy means tau on the x phase direction y. So it must be opposite to what I'm drawing. And of course, if this is acting on this direction, the opposite one must be acting, balancing the other direction. This is 12.2 megapascals. But since these two stresses make the element rotate clockwise, there must be two more stresses appearing here and here. So that everything is balanced. This is the stress state at G. Let me draw this one for H. Put this one here. And for H, first of all, let's draw the reference system. Now, if I look at this structure, this point H from the top, I am in the XZ plane, where X is going right and Z is going down. X is going right and Z is going down. Well, if I look at it from here, from this top, is X is going right and Z is going down, yes. And this is point H. So what I have is that sigma x is 70.3. It's the sum of this plus this. They are both acting perpendicular, so I take the sum of both. Uh, 70.3 megapascals. This is sigma x. Of course, I have another one in this direction. And tau xz, of course, this is now a positive stress. Let's see if I can just this. No, I can't. Okay. I have to change the arrows around. Because tau xz is z direction, so x phase that direction z. No, overall, the arrows were correct. Because x phase direction z. So this is the positive tau xz. So this is 12.2 megapascals. And this is tau xz. There you go. Okay, this concludes exercise. This concludes question 3. Just rearrange this. Now here, I have already prepared the solution of this. And we want to find the stresses at the most highly stressed point on the shaft, on the entire shaft, and show them on an infinitesimal. You may neglect the shear stress due to bending. This is exactly what we had last time. So you can neglect direct shear stress, and you may wish to draw the shear force and bending moment diagram first to identify what's the most highly stressed section. So looking at this very complex loading condition on this shaft, I can report easily this 30 kilonewton normal force here. And then I have two forces acting down on this end and two forces acting down on this end. If I sum them up, I can condense them into a single force acting down here and a single force acting down here. But these forces are also causing a twisting torque. As you can see, this force is applied to this kind of pulley mechanism that we have here. There is a 500 millimeter radius pulley here and a 300 millimeter radius pulley on this other end. So what we have is that 1800 times 500. So this twisting torque is counteracting this twisting torque, but this one is larger. So in the end, we have a 550 Newton meter twisting torque applied at this end. And of course, the other way around, since this is in equilibrium and it must be in equilibrium, this one is also the same. So 2300 times 300 minus 800 times 300 also gives 550 Newton meters. You can calculate it yourselves and find out. Okay, so overall, this is what's happening. Remember, you also need to do the free body diagram of the entire beam. So these are the two supports at B and C, and so they will react with two forces, By and Cy. So equilibrium equations let you find out how much is this force and how much is this force, which I believe should be 27. I believe that this one should be 2735 newtons. And this one should be 3100 minus 35, which, if I'm not mistaken, should be 3100 minus 35, so 3065. This one should be 3065 newtons. So you can find these ones by using equilibrium equations. It's quite easy. Now that you have this, remember you have to study this beam into 3 segments. From here to here, then from here to here, and then from here to here. So we have, I think this force goes here. And so you have, what do you have? This is A, this is B, and this is C, and this is D. So from A to B, you can find the shear force, the normal force, the twisting torque, and the bending moment diagram. From B to C, exactly the same thing. And from C to D, exactly the same thing. Now, the diagrams look like this. How do I know these are correct? Well, if I cut here and look left, there is only 2700. So this must be constant until I reach here. When I get here, I get a jump up. So I'm adding all of a sudden 2735 newtons. So this jumps up to 35 here. And then if I keep looking left from here, it's always constant because nothing is happening. And then I jump again 3065 in order to reach 3100, because if I cut and look right, it's always 3100 here. These two are very easy because this is constant. So 450 everywhere inside here, 30 and 30 everywhere inside here, and these are all positive. The bending moment is a bit more complicated, but not too much. Remember that if you might remind I might remind you that the derivative of the bending moment diagram is the shear force. Do this in green, is the shear force diagram. So we know that there is no bending moment here and no bending moment here. So it must start and end at 0. So I can take advantage of this by integrating this. So this is the slope of the bending moment. V of x is the slope of the bending moment. So we have negative slope, positive slope, very small slope, and positive slope. So negative slope means I'm reaching this much, which if you do the calculations is minus 405 Newton meters. Then I have a tiny, tiny positive slope here. So very, very, very almost horizontal from here to here. So we get at 387.5 if you do the calculations. And finally, we have this positive slope, very large, that must end up at 0 at the end of the beam. Now, if you look at this, the most stressed section of this entire structure is, of course, B. How do I know it's B? Because at B, I have one of the largest shear forces. Well, normal force is constant everywhere. Torque is constant everywhere, so I don't care about these. I only care about the shear force and the bending moment. Now, the bending moment is the largest at B. But you might argue that this one has got a larger shear force, but a smaller bending moment. Well, this is a slender shaft. So the shear given by the direct stress, the shear given by direct shear, we can neglect, as we said. So we only care about this really. But again, point B is the most stressed one. So starting from here, now that we have all the values, we have that M of B. We have that the normal force at point B is 30,000 newtons. Shear force at B, of course, the worst case scenario is minus 2,700 newtons. So approaching from the left. The twisting torque at B is 450 Newton meters. The bending moment at B is minus 405 Newton meters. And now you can just reuse all these ones all over again, exactly as we did here. So from the forces, you can find all the stresses, and then you can draw the infinitesimal at the end. So from this, you find the stresses. And from the stresses, you draw it on the infinitesimal. There you go. Now let's do the tutorial on 2D stress transformation. This is very easy, very simple. We might want to find, given a certain stress state, this was found starting from a reference system. So we must have a reference system first, and then we can find what's happening around this small element. The problem with this is that if you change the reference system, the stress state changes as well. And that's not very convenient, because you can study the same structure in 2 different ways and get different results. So that's not very convenient. So we must find a way, we know a way, to transform, to rotate the stress state from this original position to any rotation of theta angles, of theta degrees. These ones are the equations, and you can find these ones very easily by having the stress state and cutting at a certain angle. You cut at a certain angle, you get, just do the cut and look left. So all is left here is a stress that must balance the original sigma y and sigma x and tau xy. And of course, this is a normal stress, normal to the cut. And of course, you also have a parallel stress, which we call tau x prime y prime, which is parallel to the cut. Now, this one you find using this equation. Of course, as an input, you need sigma x, the original sigma x, sigma y, the original sigma y, and you need the original tau xy. And you also need the angle. This is the angle of rotation. Okay, so you need to the angle of this line, the slope, the angle of this line to find the new stress. Okay, this is very easy. So solving this, it's extremely easy. So you just have to use the equation. So let's use the equation. So for sigma x prime, let's solve D, this one, question 1D. So first of all, let's draw the infinitesimal. So if I draw the infinitesimal, let me draw it larger. This is the infinitesimal at D. And I have that sigma x is in this direction. Sorry, it's minus 60. So it's in the opposite direction. Minus 60, which of course must be balanced on the other side. Sigma y is also negative, minus 20. We call this sigma y. And tau xy is negative. Now, tau xy is negative. Remember, this is the coordinate system, which I didn't draw. Let me draw it. This is the x-axis. This is the y-axis. So tau xy is on the x phase direction y. So it's this one. So this would be a positive. This would be a positive tau xy. But since it's minus 30 megapascals, I'm drawing it in the opposite direction. So here is very easy to see that this goes in this direction. And of course, the other two must be pointing in these other two directions. So this is minus 30 megapascals, which is tau xy. Now this is the stress state, and I can just use the equations. Sigma x prime is sigma x plus sigma y, so it's sigma x minus 60 plus sigma y minus 20 divided by 2, plus sigma x minus 60 minus sigma y plus 20 divided by 2 times the cosine of 2 theta. Theta is minus 50 degrees. So we want cosine of 2 theta means the cosine of minus 100 degrees. Remember, these are degrees. Don't use radians in your calculator. Plus tau xy sine of 2 theta. Now, plus means minus 30 sine of minus 100 degrees. And this gives, according to the solution, a stress state of it should be, so it's here, -7 megapascals. We also have tau x prime y prime, which is exactly the same. It's equal to minus this. So it's basically minus this. Times sine of -100 degrees. And it's the same, minus 30 cosine of -100 degrees. And this gives a stress of 14.5 megapascals. Okay, that's very easy. And also, if you want to draw what is the new stress state, the new stress state looks like this. Rotate this 50 degrees. So this gets transformed into this. Where this one is sigma x prime, which is equal to 7, sorry, -7. Well, yes, 7 compressive. This one is 14.5, so this becomes positive now. So I have this and this and this and this. This is tau x prime y prime, which is 14.5 megapascals. And this is, of course, x prime and y prime, the new axes. And the difference between these new axes and the old axis, so the rotation, is 50 degrees. $50 clockwise, of course. That's it. So you just can solve all the other ones in exactly the same way. It's just a matter of using your calculator. Now, before I leave you, I want to discuss the Morse circle. Morse circle is just the graphical representation of these equations. So the graphical representation of these equations, and you can draw the Morse circle by just following these simple steps. So first step is draw the axes, sigma tau, and we draw them with sigma going in this direction and tau going down for historical reasons and for convention, really. Then we want to, let me do this down here. Then we want to find point A with coordinates sigma x, comma, tau xy, and then find point B with coordinates sigma y, tau yx, which is of course equal and opposite to tau xy, and finally connect them using a diameter. Find the center, draw the circle. So these are the 6 steps. So let me do them one by one, and let's use this one that we just solved to find the Morse circle. So let's find point A. Point A is, okay, so first of all, let me say that this is the sigma axis. And this is the tau axis. And I know that the tau axis goes in counterclockwise way here and clockwise way here. So sigma x and tau xy. Now sigma x is negative 60. So let's say that my unit is this one. So my unit is this. This length is 10 megapascals. And so I have 60s, 1, 2, 3, 4, 5, 6. So this point here is 60. 2, 3, 4, 5, 6 should be this. This is 60 minus 60 megapascal. This is sigma x. And of course, tau xy is 30 clockwise. So it's minus 30. So 1, 2, 3 here. So if I just draw the lines, I can find point A. This point here is my point A, which has coordinates sigma x, tau xy. Let me not draw the coordinates. Let me draw point A here. Let me find point B. Point B is at sigma y, so minus 20, and tau yx, which is of course 30. Now y is 1, 2, 3. This is 30. And sigma y is minus 20, so it's here. So just draw these lines. And so this is point B. Now, step 4, connect them using a diameter. So I'll just draw a straight line that goes from A to B. Straight line that goes from A to B. So I can find where is the center C. Now the center C must lie on the sigma axis, must lie on this axis, because we have minus 30 and plus 30 here. So this is also a diameter, because it's the circle is symmetric around the sigma axis, having minus 30 and 30, because A and B both belong to the circle. And so that means it must lie, the center must lie on the sigma axis. So now that we have the center and A, I can point my compass here and here and draw the circle. And now I'll do this digitally as best as I can. No. No. Come on. There you go. And now I make sure that I can make it pass through A and B. I make it pass through A and B. More or less. There you go. This is the Morse circle. I know that A and B are on the same diametral line, and this indicates my 0 degrees. This indicates the stress state here when I am not in a non-rotated state, 0 degrees of rotation. Now, if I want to rotate to find what is, remember this one was sigma y, and this is tau yx, this is tau xy, and this is sigma x. So if I want to find what happens after a rotation of 50 degrees, remember, clockwise, I must rotate this diametral line, I must rotate it 100 degrees. Why 100? Because the Morse circle is a representation of this equation, and in this equation, all the angles are doubled. This reflects the 180 degrees symmetry of the stress element. As you can see, if I rotate this by 180 degrees, I'm not changing anything. And so this is reflected in the plane by rotating 360 degrees. Of course, this also means that the sine and cosine gives you exactly the same values. So this effect is encoded in this way. And so let me draw this rotated version of this is, let's say this is 100 degrees. So I'll say that this rotation here this angle is 100 degrees to theta. And of course, it's a rotation, it's a clockwise rotation, so that's minus 100 degrees. And now that I'm here, this is my new point B prime. And this is my new point A prime. And so I know that A prime has coordinates tau x prime y prime and coordinate sigma x prime. And B prime has coordinates, sigma y prime, and of course, tau y prime x prime, which is, of course, it must be exactly the same as tau x prime. So we can see this is circa 10 megapascals, which if we look at it, it's 14.5 here. Okay, so almost the same. Okay, two more important diameters that we can take are the maximum shear stress diameter, which is this one. The vertical diameter of the Morse circle is extremely important because it gives you tau max, well, negative tau max and positive tau max, which are of course the same number, just one is positive, one is negative. So the maximum shear stress that the infinitesimal element can experience given a certain rotation. So you can also find how much you have to rotate, this original diametral line in order to have pure shear stress with a residual normal stress. And of course, in the other side, the other important diametral line is this one, this horizontal one, as you might imagine. This one is sigma max, which we also call sigma 1. And this one is the smallest normal stress that the element can experience, sigma min, also called sigma 2. Now these ones, sigma 1 and sigma 2, are called principal stresses. So if you rotate the element by 2 theta p angle in the opposite direction, in a clockwise direction, you end up in a state of stress that is perfectly normal stress. There is no shear stress. See, all these ones lie on the sigma axis where tau is 0. So you can find with the rotation of 2 pi. So let me do this. Let me copy this. So with a certain rotation of 2 theta p, you can find pure, these are both negative. As you can see, they are both in the negative sigma axis. So sigma 1 and sigma 2 are both negative. So in this case, I can just change these colors. And I have that this is sigma 1, and this is sigma 2. Or alternatively, in the other sense, let me change this to this as well. So this is the state of stress. It's called principal stress state. And conversely, I can just copy this. Well, I'll copy this one again because it contains also the arrows I'm interested in. Conversely, for this other stress condition, you have a maximum shear stress, but you also have some normal stress. See, because it's a negative normal stress. They are all the same. So they have all the same length. And these ones. Oops. This is called maximum shear stress state. Okay, now this concludes the tutorial. Thank you very much, and I'll see you next week. Bye-bye.